How did fundamental electrical units evolve for electrical measurement? Imagine trying to measure something invisible like electricity before there were any standards. It would be like trying to weigh air or measure time with a sundial. Over time, scientists needed reliable ways to quantify electrical phenomena. The journey began thousands of years ago when ancient Greeks noticed static electricity by rubbing amber. But it was only in the 1800s that scientists started to understand and measure electricity systematically. Alessandro Volta invented the voltaic pile, the first chemical battery, which gave a steady current. This was a big step because it allowed consistent experiments. Then, in 1826, Georg Simon's Ohm came along and formulated Ohm's law. This law explained how voltage, current, and resistance relate, giving scientists a way to measure and compare electrical quantities. It was like creating a language for electricity. A few years later, Michael Faraday discovered electromagnetic induction, showing that changing magnetic fields could generate electric currents. This discovery led to electric generators and transformers, which needed precise measurement tools. As technology advanced, international groups began to define standard units. They created the volt for voltage, the Ampere for current, the Ohm for resistance, and the Coulomb for electric charge. These units were based on physical phenomena, like the force between two current-carrying wires for the Ampere. The 1881 International Electrical Congress helped unify these standards worldwide, making sure everyone measured the same way. To make calibration easier, physical standards were developed, such as mercury cells for voltage and silver voltmeters for current. These provided reproducible benchmarks for calibrating test equipment. As science progressed, the units evolved from electromagnetic-based measures to the International System of Units, which linked electrical units to mechanical ones. In the 20th century, quantum physics brought in new standards. The quantum Hall effect and Josephson effect allowed for extremely precise measurements of resistance and voltage. This meant electrical measurements could be incredibly accurate, which is essential for modern electrical engineering. When engineers calibrate test equipment today, they compare their instruments to these standards. This ensures measurements of voltage, current, and resistance are correct and traceable. It's like using a ruler to measure length. You need a standard to be sure. The story of how electrical units evolved shows how science and technology work hand in hand. From ancient observations to quantum standards, each step made electrical measurement more reliable and precise. This ongoing process helps engineers design safer, more efficient electrical systems.